Hey guys, so today we're going to go through the natural base. We have these to do now. Obviously, we're going to do that in class. And we're going to take a look at this graphing. And this is actually kind of where Euler's number came from. This natural number of E came from 1 plus 1 over x to the x power. And that's why it's built into our exponential section, because it is an exponential function. And if you notice, and we did this in class, that as you continue to increase your x values, the number along the y is getting closer and closer and closer to 2.7183. And that ends up being E, this natural number, or the Euler number, that is going to be of importance as we go through this section. So like I said, it approaches this 2.71828 value. It is called the Euler number. It's the letter E, a lowercase e, and it's basically an irrational number, just like pi, right? So pi, we know, is 3.14159. It keeps going on and on forever, and we can use the symbol pi to represent it, just like we're going to use the symbol E. And because it's a variable that it represents something, we can use exponent rules just like we normally would. So multiplication, we can add the exponents. If we divide, we can subtract our exponents. We can do distributive property with the exponents. So we can apply all exponent rules just as we normally would with any variable with the letter E, even though it represents something. Okay, and again, we'll go through each of these in the class period, but we would just add in the first one, we would reduce the fraction and subtract the exponents in the second one, and then distribute that 3 on the inside in the third one. Okay, with our exponentials, we know we have a growth and a decay. Same thing with our natural base. However, since E is 2.718, it is always, it is always going to be a positive growth, a larger base, right? We're always going to have this 2.718 base, which makes it a growth. However, the exponent, the rate of this E value, is what's going to determine if it's a growth or a decay. So if we have a positive R value, if we have a positive exponent, that's a growth because we have a larger number. That 2.718 is going to be to a positive power, which will make it bigger and keep it positive. If the R is negative, remember with negative exponents, it just means it's a fraction. It's just a reciprocal. So if I have a negative exponent, say I have e to the negative 2 power, that's really 1 over e to the second power, which now makes it a number less than 1. It's a fraction. It's 1 over something. So that is now a decay function. Okay, so again, we have our growth and decays, and it's going to be dependent on the rate whenever we're using E for our function. Okay. And we'll go through and graph these. We're going to use Desmos. You're going to use your graphing function, the table function in Desmos to fill in those tables. You plot the points. Just remember your domain and range. Domain will be always all real numbers because I can plug any x value I want, and I'm going to get a value for the y. And for the most part, remember, we only talk about the range. Range will always be y is greater than 0 unless we are adding or subtracting something to the end. We have some k value that's going to rise or lower your function. In both these cases, we don't. So we have a domain of all real numbers, and we have a range of y greater than 0. Again, we'll go through all of those examples in class. And the last thing I'm going to talk about is our real world problems. Okay, we had a growth formula for compounding things. Well, we now have one where it compounds it continuously. So instead of doing it every day or every month or every week, like we were looking at before, now every moment, it is continuously, at every moment of time, it is going to compound your income or whatever you put into your account. So in this problem, or in this formula, PERT, going to be your easy way to remember it, P is your starting principal. Whatever amount you're putting into that account. E is going to be our Euler number. R is the rate as a decimal, so don't forget that. You're going to change any given rate to a decimal. And T is your time in years. Once you have all that figured out, it's a matter of using your calculator. So you would use Desmos, plug it in, and find out what becomes of your A value. What do you get after that certain time frame? So, for example, if I have, my pen will write, I have $2,500 in my savings account for college, 7.2%. So I'm going to change that, right? You move it two places, 0.72. 0.072 is going to be my percent. And we have 7 years. So when we plug it in, the principal, the P part was 2,500. E is always going to be there. The rate, 0.072 times the number of your years. And again, from there, it's just a matter of plugging it in your calculator and then being able to find out what it is after that time frame. Okay. All right, and we'll go through some more examples of that and talking about comparison to graphs. Now with this one, just a little FYI, we have P, a principal value of 4,500. In the first one, I have an A value of 4,000. In the second one, that is your P. That is your principal rate that you're going to be using for the graph function. Now, I don't know the rate in which it's moving, but I do know it's going to be 4,000 E to some rate over time. Okay, whereas this case, I can see the 4,500 and I can see its rate of 4% because of the 0.04. Okay. And this is the last thing we're going to talk about is rewriting things from growth and decay models. Okay, we did this previously with regular growth and decay. We can do it with the E functions. It's the same process. You're still going to pull apart the rate and the exponent so that way the exponent can be by itself. You will then take this E to the negative 1.2 in this case, put it in your calculator, evaluate it. Once you have that value, I'm going to suggest going to 4 decimal places just for consistency and to make sure you get a value that makes sense. And then once you decide whether it's a growth or a decay, you're going to set this new value equal to 1 plus R if it's a growth, or 1 minus R if it's a decay. And then you'll be able to find your rate. So in this problem, I knew it was a decay because it was a negative exponent. So when I got that E value, I set it equal to 1 minus R, solved it, and I got R is 0.6988. I could rewrite it in my format, and then I can see that the rate, the decay rate, is 69.88%. So that's decreasing by that amount. And we can do the same thing, whether it's a growth function or a decay function. You are simply going to separate the values. Go back to that one, actually. Simply going to separate them like we see here. We took apart the negative 1.2 from the X. Then I completely separated it by putting it in a grouping before I even found that. And this part right here is simply just calculator work. Okay, you put that in a calculator. You don't have to worry about figuring out what is E to that negative 1.2. You put it in a calculator and then set it equal to 1 minus R if it's a decay, negative exponent, or 1 plus R if it's a growth, a positive exponent.